Hello. Whether you're winding down for the night, looking for something calm to listen to, or just need your mind to settle, you're in the right place. This is Sleepless Veteran. Military history told slowly, carefully, without drama or urgency. Just facts, just understanding, just history unfolding at a pace that lets you rest. Tonight, we're going to look at a tank, the T-72, a Soviet design from 1971 that became one of the most produced tanks in history. Tens of thousands built, exported to dozens of nations, used in conflicts across 5 decades, from the deserts of Iraq to the streets of Grozny to the fields of Ukraine. The T-72 has been there, still is there, still in service, still being used. But this isn't a story about battlefield victories or tactical brilliance. This is a story about design. About choices made in a design bureau in Nizhny Tagil in the early 1970s. About what those choices meant for the young men who would crew these tanks. About the trade-offs accepted to make a tank that was cheap, simple, and producible in enormous quantities. About what happens inside when the armor fails and a projectile reaches the ammunition. This is about the space inside. About 3 men working in an interior so cramped that movement is measured in inches. About temperatures that reach 120 degrees in summer and drop below freezing in winter. About sitting directly above the ammunition. About knowing what that means. About the instant when penetration occurs and the propellant detonates. About why the turret separates from the hull and is thrown skyward. About why no one survives when this happens. We're not here to judge or condemn. Not here to make war seem simple or to assign blame. Just here to understand. To see how a machine was designed. How it worked. What it required of the people inside. What happened when it failed. The T-72's story is technical and human both. Is about steel and explosives and also about the men who lived and died inside this design. So settle in. Get comfortable. What follows is calm and steady. We'll move through this history together, from the outside of the tank to the inside, from the design philosophy to the human experience, from the mechanism that loads the gun to the catastrophic explosion that ends everything, from the conflicts that demonstrated the vulnerability to the reasons it was never fixed. This is the story of the T-72. Of the choices that created it, of the consequences that followed, of the crews who climbed inside knowing or not knowing what those consequences were. Take your time. Breathe slowly. Let's begin at the beginning. Let's start with what the tank looks like from outside. With the profile that determined everything else. With the 7 feet that changed what it meant to be inside. The T-72 main battle tank sits low to the ground. From the bottom of the tracks to the top of the turret measures approximately 7 feet. 7 feet total height. For comparison, the American M1 Abrams stands at 8 feet. The British Challenger at similar height. The German Leopard 2 reaches 8 feet as well. 1 foot of difference, 12 inches. That difference defined everything. The tank from outside appears conventional. Recognizable as a tank immediately. Turret centered on the hull. Long gun tube extending forward, the 125mm smoothbore. Tracks on either side. Road wheels, drive sprocket, return rollers. The basic geometry of a tracked armored vehicle. Nothing obviously unusual. Nothing that would make someone unfamiliar with tanks notice anything strange. But that low profile, that 7 feet, that measurement was deliberate, was the result of specific design goals. The Soviet military wanted a tank that was difficult to spot, difficult to hit, a smaller target, lower to the ground. The reasoning was straightforward. Tank combat often occurred at long ranges. A lower profile meant less of the tank visible, especially when hull down. When positioned behind cover with only the turret exposed, every inch of height mattered. Every inch made the target smaller, made hits less probable. The T-72 entered Soviet service in 1971. The design work occurred in the late 1960s. The design bureau was Uralvagonzavod in Nizhny Tagil, an industrial city in the Ural Mountains. The lead designer was Valery Venediktov. The design philosophy came from decades of Soviet armor doctrine, from lessons learned in the Second World War, from analysis of what future war would require, from assumptions about how tanks would be used, how many would be needed, what they would face. The specifications beyond height were competitive for the era. The main gun could fire armor-piercing rounds, high-explosive rounds, even anti-tank guided missiles through the gun tube. The fire control was adequate, though less sophisticated than Western equivalents. The armor protection was revolutionary. Composite armor, layers of steel and non-metallic materials in the glass's plate and turret front. Protection that could defeat contemporary anti-tank weapons when facing frontal attacks. The sides and rear were thinner, more vulnerable. But Soviet doctrine assumed tanks would fight from the front, would present frontal armor to the enemy. Side and rear protection were sacrificed for weight savings. The engine was a V46 12-cylinder diesel, multi-fuel capable, could run on diesel, gasoline, kerosene, or jet fuel. The flexibility simplified logistics. The engine produced 780 horsepower initially. Later variants increased this. The power-to-weight ratio allowed speeds of 60 kilometers per hour on roads, approximately 37 miles per hour. Cross-country speed was lower but acceptable. The mobility was adequate. Not exceptional but sufficient for Soviet doctrine, which emphasized breakthrough and exploitation. The production numbers were extraordinary. Over 25,000 T-72s were manufactured in the Soviet Union and Russia. Thousands more were produced under license in Poland, Czechoslovakia, Yugoslavia, India, and Iran. The export market was extensive. Syria purchased them, Iraq purchased them, Libya, Angola, dozens of nations. The T-72 became ubiquitous, became the standard Soviet export tank, became the vehicle that represented Soviet armor design to the world. But all of this was determined by that initial choice, 7 feet. To achieve that height, everything inside had to be compact, compressed, fitted into a volume that was barely sufficient. The crew positions had to be redesigned. The ammunition storage had to be reconsidered. The loader position had to be eliminated. Everything flowed from that one measurement, from the decision to make the tank as low as possible, as small as possible, as difficult to hit as possible. The external appearance didn't reveal the compromises, didn't show what achieving 7 feet cost. From outside, the T-72 looked capable, looked substantial. The armor appeared thick. The gun appeared powerful. The overall impression was of a competent main battle tank. Nothing suggested the interior conditions. Nothing indicated the vulnerability that the design created. The exterior was deceptive in its conventionality. Only by going inside, only by understanding how the space was used, only by seeing what the crew lived with. Only then did the consequences of that 7-foot height become clear. The low profile worked, tactically. The T-72 was harder to spot than taller tanks, was harder to hit at long range. The design goal was achieved, but achievement came with cost, with trade-offs, with decisions that seemed reasonable in the design bureau. That made sense on paper, but that would prove catastrophic when the armor was penetrated, when the enemy round reached the interior, when the design's fundamental vulnerability was exposed. Standing next to a T-72, looking at it from outside, none of this is obvious. The tank looks formidable, looks dangerous to face, looks protective of its crew. Only later. Only when understanding how the interior is arranged. Only when seeing what happens when penetration occurs. Only then does the profile reveal its full cost. The 7 feet that made the tank harder to hit also made it impossible to survive once hit in the wrong place. The design decision that seemed like pure advantage, that appeared to have only benefits, carried consequences that wouldn't be fully understood until combat, until crews climbed inside, until projectiles penetrated, until the ammunition detonated and the turrets began separating from holes. The crew approaches the T-72 for daily operations. 3 men, the commander, the gunner, the driver. In Western tanks, there would be 4. Commander, gunner, loader, driver. But the T-72 has no loader. The elimination of this position was fundamental to the design, made the small turret possible, made the low profile achievable, but also created the conditions that would define crew vulnerability. Entry is through hatches. The driver's hatch is in the front of the hull, forward and to the left. The hatch is small, the driver lowers himself through. Feet first, finding the position, settling into the seat. The position is immediately unusual. The driver doesn't sit upright, doesn't have a conventional driving position. Instead, the seat is reclined, nearly lying down. The driver operates the controls while reclined at approximately 45 degrees, almost flat. This position exists because of the low profile. The hull height had to be minimal. A conventional upright driving position would require more internal height, would add inches to the overall height. Unacceptable. So the driver lies back, looks forward through periscopes, small viewing blocks. The visibility is limited, narrow fields of view. The driver must move his head to see different areas, must scan constantly. The periscopes can be damaged by debris, by vegetation, by enemy fire. When this happens, visibility becomes nearly impossible. The space around the driver is tight, cluttered. Controls for the transmission, levers for steering, gauges for monitoring engine temperature, oil pressure, fuel. The lighting is dim. The ventilation is minimal. In summer, the heat is immediate. The metal hull conducts heat from outside. The engine behind the driver's position radiates heat forward. Within minutes of the engine starting, the driver's compartment becomes hot. Uncomfortably hot. In Middle Eastern climates, the temperature would reach levels that tested human endurance. The commander and gunner enter through turret hatches. The commander's hatch is on the right side of the turret, the gunner's on the left. Both hatches are relatively small. The crew members lower themselves through, down into the turret interior. The first impression is confinement. The space is smaller than expected. Even for those who've seen photographs, even for those who've trained on the tank, the reality of the interior space is always surprising, always more cramped than imagined. The commander's station is on the right side of the turret. The seat is adjustable, can be raised for head-out operation with the hatch open, can be lowered for head-in operation with the hatch closed. In combat, the hatch would be closed. The commander would be inside, surrounded by equipment. The fire control system, the radios, the intercom, the observation periscopes, the cupola that allows rotating views. Everything is close, within arm's reach, but so close that movement requires care. Elbows bump into equipment, knees contact, controls. The crew learns to move economically, minimally, to stay in position as much as possible. The gunner's station mirrors the commander's on the left side. The gunner faces forward, has the primary gun sight, the controls for turret traverse and gun elevation, the triggers for the main gun and coaxial machine gun. The space is similarly cluttered, similarly tight. The gunner's seat is also adjustable, but the range of adjustment is limited. The gunner works hunched slightly forward, looking through the sight, hands on controls. The position becomes uncomfortable during extended operations. Backs ache, necks stiffen, but there's no room to stretch, no space to stand, no relief from the position until operations end. Between and beneath the commander and gunner is the carousel, visible from inside the turret, a mechanical ring approximately 6 feet in diameter. The autoloader, the mechanism that eliminated the need for a fourth crew member. The carousel holds 22 rounds, each round in two parts, the projectile in one position, the propellant charge in another. The rounds lie horizontally in the carousel, arranged in two concentric circles. The mechanism can rotate, can position any round beneath the gun breech for loading. The crew can see the carousel, can see the tops of the propellant charges, fabric bags, beige or green, containing the explosive propellant that will launch the projectile. 22 of these charges, visible, right there, beneath the crew stations. The commander sits above and to the right of them, the gunner above and to the left. The driver is forward, but the carousel extends forward as well, close to the driver's position. The ammunition isn't in a separate compartment, isn't isolated, isn't protected by armored barriers. Just there, part of the interior space, part of the environment where the crew works. Additional ammunition is stored elsewhere, in racks in the hull, in positions in the turret. The total capacity varies by model. 39 rounds in some versions, 28 in others, but the carousel rounds are the most accessible, are the ready rounds, are the ones that will be fired first, are also the ones most likely to detonate if the tank is penetrated, the ones that sit directly beneath where the crew spends their time. The interior lighting is poor, small lights, dim. The visibility relies mostly on natural light from the periscopes when hatches are closed. At night, the interior is dark. The crew works by feel, by memory, by familiarity with where every control is, where every switch is. The darkness adds to the confinement, makes the space feel smaller, makes awareness of the surroundings difficult. The smell is distinctive. Oil, diesel fuel, metal, sweat. The ventilation is inadequate. The air is stale. The crew smells this constantly, becomes accustomed to it, stops noticing eventually. But initially, the smell is overwhelming, is part of the environment, part of what makes the interior feel industrial, mechanical, inhospitable to human presence. The crew settles into their positions. Commander in his seat, gunner in his, driver reclined below, each connected to the intercom. Headsets on, testing communication. The engine hasn't started yet. The interior is relatively quiet. This is as good as conditions get. Once the engine starts, once operations begin, the environment will deteriorate, will become louder, hotter, more uncomfortable. But for now, in this moment before starting, there's a brief pause. A moment to prepare, to check equipment, to ensure everything is ready. This is the workspace. This is where the crew will spend hours, will operate, will fight if necessary. This cramped, cluttered, poorly ventilated interior. This space measured in inches. This environment where movement is restricted and comfort is impossible. This is what achieving 7 feet of height required. This is what eliminating the loader created. This is what the crew accepted, what they worked in, what they lived with, what they would die in if penetration occurred, if the propellant charges beneath them were struck, if the design's vulnerability was exploited. The interior didn't feel dangerous, didn't seem threatening, just uncomfortable, just cramped. The danger was hidden, was potential, was waiting for penetration, for the instant when the interior space would transform from uncomfortable workspace to fatal trap. The autoloader carousel is the defining feature of the T-72, the mechanism that makes the 3-man crew possible, the system that eliminated the loader position, the design that created the tank's fundamental vulnerability. Understanding the carousel requires understanding both its function and its location, both what it does and where it does it. The carousel is a ring mechanism, approximately 6 feet in diameter, located in the turret basket. The basket is the floor of the turret that rotates with the turret when it traverses. The carousel sits beneath the turret floor. below the level where the commander and gunner sit, but not far below. The crew positions are directly above it. The commander's seat is mounted so that the carousel is beneath and slightly forward. The gunner's seat similarly positioned on the opposite side. The driver in the hull is forward of the carousel but close to it, within a few feet. The mechanism holds 22 rounds. Each round consists of two parts, the projectile and the propellant charge. These are stored separately, in different positions within the carousel. The projectiles are the actual munitions. Armor-piercing, fin-stabilized, discarding sabot rounds. High-explosive anti-tank rounds. High-explosive fragmentation rounds. Different types for different targets. Each projectile weighs approximately 20 to 25 kilograms, 45 to 55 pounds. Metal, dense, solid. The propellant charges are different. These are fabric bags, canvas or similar material, containing the explosive propellant, the chemical compound that will ignite and expand rapidly, that will create the gas pressure that drives the projectile down the barrel. Each charge contains several kilograms of propellant. The amount varies by ammunition type. Some rounds require more propellant, some less, but all contain explosive material measured in kilograms. All are capable of detonation if subjected to sufficient heat or impact. The storage arrangement is horizontal. The rounds lie flat in the carousel, arranged in two concentric circles, an inner circle and an outer circle. The projectiles in one set of positions, the propellant charges in adjacent positions. The carousel can rotate. Electric motors turn it. The rotation positions the selected ammunition type beneath the gun breech, beneath the loading mechanism. The loading sequence begins when the commander or gunner selects an ammunition type. Armor-piercing, high explosive. The selection is made through controls. The carousel receives the signal, begins rotating if necessary, positions the correct ammunition beneath the breech. The rotation takes seconds. Once positioned, the loading mechanism activates. The mechanical arm extends downward into the carousel, grips the projectile, lifts it, aligns it with the breech, rams it forward into the gun. The projectile seats, then the arm retracts, extends again, grips the propellant charge, lifts it, rams it into the breech behind the projectile. The breech closes. The gun is loaded, ready to fire. The entire cycle takes approximately 8 seconds for the first round, 6 to 7 seconds for subsequent rounds if the carousel doesn't need to rotate far, if the next selected round is adjacent to the previous round. The rate of fire is competitive with human loaders in Western tanks. A well-trained loader can load in similar time, 5 to 6 seconds. The autoloader provides consistency, doesn't fatigue, doesn't slow down during extended engagements, but also can't adapt, can't improvise, can't clear malfunctions easily. The advantage of the autoloader was elimination of the loader position. In Western tanks, the loader is the fourth crew member, stands in the turret, physically lifts rounds from storage, loads them into the breech. Hard physical work, requires strength, requires speed, requires endurance. The loader must maintain performance during extended combat, must work in cramped turret, must handle heavy ammunition repeatedly. The position is demanding. Eliminating the loader meant 3 crew instead of 4, meant the turret could be smaller, didn't need space for a 4th person to stand and work, didn't need the volume required for a human loader to move and function. The turret could be lower, more compact. The overall height could be reduced. The low profile became achievable. The weight decreased. The production cost decreased. Fewer crew members to train per tank. For an army built on conscription, this mattered. Meant more tanks could be fielded with the available manpower. Meant faster training pipeline. Meant simpler logistics. But eliminating the loader meant the autoloader was necessary. Meant the carousel had to be installed. Meant the ammunition had to be stored in the carousel. Meant the ammunition had to be in the turret basket. Beneath the crew, 22 rounds, 22 projectiles, 22 propellant charges, 44 pieces of ammunition total, all in the carousel, all beneath and around the crew positions. The propellant charges are the vulnerability. The projectiles themselves are relatively stable, are solid metal mostly, don't detonate easily, can be struck without necessarily exploding. But the propellant charges are different, are explosive by nature, are designed to ignite and burn rapidly, are sensitive to heat, to impact, to fragments. If a penetrating projectile strikes the carousel, if it hits a propellant charge, the charge will detonate. When one propellant charge detonates in the carousel, the others detonate sympathetically. The explosion of one creates sufficient heat and pressure to ignite the adjacent charges. Those detonate, create more heat and pressure, ignite more charges. The progression is nearly instantaneous. All 22 propellant charges detonate within fractions of a second. The combined explosion releases enormous energy, the equivalent of dozens of kilograms of high explosive detonating simultaneously in the turret basket, beneath the crew, in the crew compartment. The carousel is visible to the crew, can be seen from the turret positions. The tops of the propellant charges are right there, below the turret floor but visible through the mechanism. The crew works above this, sits above this, knows what's beneath them. Some crew members thought about this constantly, thought about what penetration would mean, what hitting the carousel would cause. Others developed fatalism, accepted the risk, focused on their jobs, tried not to think about the ammunition beneath them, about what would happen if hit there. The design was effective for its purpose. The autoloader worked, was reliable when maintained, could load consistently, could sustain rate of fire, allowed the three-man crew, allowed the small turret, allowed the low profile, achieved the design goals, but also created a condition where the crew worked in constant proximity to explosive charges that were not protected from the crew compartment, that were not isolated, that were not equipped with any mechanism to vent explosion away from the crew. The carousel was both the solution to the design problem and the creation of a fatal vulnerability, was both innovation and catastrophe, was both success and failure, depending on whether the armor held, depending on whether penetration occurred, depending on whether the round that penetrated struck the carousel, on factors the crew couldn't control, on probabilities they could only hope favored them, on luck that they needed but couldn't guarantee. The engine starts. The V46 12-cylinder diesel comes to life. The sound is immediate, loud, deep, rough. The entire tank vibrates. The crew feels it through their seats, through the floor, through every point of contact with the vehicle. The noise level rises dramatically. Conversation becomes impossible without the intercom. The crew switches to headsets, speaks through microphones, listens through earphones, but the engine noise comes through anyway, penetrates the headsets, becomes background to everything. The temperature begins changing immediately. The engine produces heat. 780 horsepower generates enormous thermal energy. The engine compartment is behind the crew compartment, separated by a firewall, but the firewall isn't perfect insulation. Heat conducts through, radiates into the crew areas. Within minutes, the interior temperature begins rising. The metal hull and turret absorb heat from the engine, from the sun if daytime, from the friction of moving. The metal radiates heat inward. The crew begins sweating. In temperate climates, the heat is manageable, uncomfortable but endurable. The crew drinks water, wears minimal clothing under uniforms when possible, works through the discomfort, but in hot climates, Middle Eastern deserts, Southeast Asian tropics, the heat becomes extreme. The interior temperature can exceed 120 degrees Fahrenheit, sometimes higher. The metal surfaces become too hot to touch with bare skin. The air becomes thick. Breathing feels labored. The crew sweats profusely. Dehydration becomes constant risk. Heat exhaustion is possible. Heat stroke is possible if the crew can't cool down, can't get relief. The ventilation system is minimal. Small fans, limited airflow, not sufficient to cool the interior, not sufficient to exchange the air adequately. The air becomes stale. Smells of diesel fumes, oil, sweat, metal. The crew breathes this, works in this. The smell becomes normalized, becomes part of the environment. But it indicates the air quality, the lack of fresh air circulation, the inadequacy of the ventilation for the heat and the crew's needs. In cold climates, the problem inverts. The metal hull and turret conduct cold. The thin metal provides minimal insulation. The interior temperature drops. The heating system exists but is often inadequate. Small heaters, not sufficient to warm the entire interior. The crew wears heavy clothing, multiple layers, insulated suits, but still suffers from cold. Hands become numb. Feet lose sensation. Operating controls with numb fingers is difficult. Requires concentration, requires effort. The cold saps energy, makes everything harder, makes the crew's performance degrade. The driver's position has additional challenges. The reclined position is uncomfortable for extended periods. The driver can't sit up, can't stretch. The position causes back strain, lower back particularly. The driver must maintain this position for hours during operations. Must drive the tank, must navigate, must watch through the limited periscopes, must coordinate with the commander, all while reclined, all while fighting the discomfort, all while managing the physical strain of the position. The visibility from the driver's position is limited. The periscopes provide narrow fields of view. The driver must move his head constantly, must scan, must piece together understanding of the surroundings from limited inputs. At night, visibility decreases further. The driver relies on whatever lighting is available. Sometimes infrared systems, sometimes just ambient light, sometimes nothing. Driving in darkness with limited visibility requires skill, requires experience, requires confidence in the vehicle's ability to handle terrain the driver can barely see. The commander and gunner in the turret face different discomforts. The seats are adjustable, but the range is limited. The positions are upright but hunched, looking through optics. Operating controls. The turret is cluttered, equipment everywhere. The space is tight. Elbows bump into controls. Knees contact structure. Movement must be careful, deliberate. The crew learns to minimize movement, to stay positioned, to avoid disrupting equipment, to avoid causing problems. The psychological environment is as significant as the physical. The crew works in close proximity, 3 men in cramped space. Personal space doesn't exist. Privacy doesn't exist. The crew is together constantly during operations. Can't separate. Can't have individual space. The relationships matter. The crew dynamics matter. A crew that functions well together can manage the environment better, can support each other, can maintain morale despite the conditions. A crew with personality conflicts suffers more. The environment amplifies friction, makes tensions worse, makes everything harder. The knowledge of the ammunition is psychological weight. The crew knows the propellant charges are beneath them, knows what penetration could mean. Some crew members think about this constantly. Can't ignore it. The knowledge creates anxiety, creates fear, makes every engagement feel more dangerous, makes every incoming fire more threatening. Other crew members develop different psychology. Accept the risk, understand it intellectually, but don't dwell on it. Focus on their jobs. Focus on what they can control. Trust the armor. Trust their training. Trust luck. The noise is continuous. The engine runs constantly during operations. The sound never stops, never decreases. The crew operates in this noise for hours. The effect is fatiguing, makes concentration harder, makes communication difficult even with intercom, makes awareness of surroundings challenging. The crew learns to function despite the noise, learns to hear what matters through the headsets, learns to interpret sounds, to recognize normal engine sounds versus abnormal, to detect problems through acoustic changes. But the learning doesn't make the noise less fatiguing, less wearing, less exhausting. Extended operations mean the crew lives in or near the tank, eats in the tank, sleeps near the tank. Personal hygiene suffers. Washing is minimal. Opportunities are limited. The crew becomes dirty, smells. The close quarters make this worse, make the environment more unpleasant. But this is accepted, is part of field operations, part of what military service in armored units requires. The crew endures, continues, functions despite the conditions, despite the discomfort, despite the psychological weight, despite everything. This is what it means to crew a T-72. This is the daily reality, the environment that the design created, the conditions that achieving 7 feet of height and 3-man crew required, the cost of the low profile and the autoloader and the small turret. The crew accepted this because it was their assignment, their duty, their job. They climbed into this environment, worked in it, fought from it, lived in it during operations, endured heat or cold, endured noise, endured confinement, endured the knowledge of what sat beneath them, endured because they were crew members, because this was the tank they were assigned, because this was what service required. The environment was hostile, was difficult, was exhausting, but the crew managed, continued, operated, until penetration occurred, until the armor failed, until the design's vulnerability was exposed, until the environment transformed from difficult to fatal in the instant of ammunition detonation. The T-72 was designed in the context of Soviet military doctrine. Understanding why it was designed the way it was requires understanding what the Soviet military believed about future warfare, what assumptions guided design decisions, what priorities determined trade-offs. Soviet doctrine assumed large-scale conventional war in Europe primarily, against NATO forces. The doctrine emphasized mass, overwhelming numbers, breakthrough operations. The concept was that Soviet armor would concentrate at specific points, would breach NATO defenses through sheer weight of numbers, would exploit breakthrough rapidly, would advance deep, would disrupt NATO's ability to respond, would win through speed and mass rather than through technological superiority of individual vehicles. This doctrine had roots in World War II experience. The Red Army had learned that numerical superiority could overcome tactical disadvantages, had learned that tank armies could exploit breakthroughs, could advance hundreds of kilometers, could encircle enemy forces, could win through operational tempo and mass. The T-34 had embodied this philosophy, was simple, was producible in enormous quantities, was good enough to accomplish missions despite individual limitations. The doctrine that emerged from this experience emphasized quantity, emphasized breakthrough, emphasized exploitation, emphasized accepting casualties to achieve objectives. The Cold War context reinforced this doctrine. NATO had technological advantages, had better electronics, had better fire control in many systems, had better training often. The Soviet Union couldn't match NATO tank for tank in quality. The industrial base couldn't produce tanks as sophisticated as Western designs at comparable cost. The economy couldn't support equivalent investment per vehicle. The technological gap was real, was acknowledged, was factored into planning. The Soviet answer was numbers. If NATO had better individual tanks, the Soviet Union would field more tanks, would overwhelm through mass, would accept higher loss rates, would rely on weight of numbers to achieve breakthrough. The calculation was strategic, was based on industrial capacity, on economic reality, on what was achievable given Soviet resources and technological base. This assumption drove design philosophy. The T-72 needed to be producible in vast quantities, needed to be simple enough that wartime production could expand rapidly, needed to be cheap enough that thousands could be afforded, needed to be simple enough that conscripts with minimal training could operate them effectively. Every design choice was evaluated through this lens. Does this choice make the tank more producible, more affordable, simpler to operate? If yes, the choice was favored. If no, the choice was reconsidered. The conscription system was fundamental to Soviet military planning. The Red Army relied on conscripts, young men serving mandatory terms, typically 2 years, sometimes 3. The turnover was constant. Experienced soldiers left service. New conscripts arrived. The training pipeline was continuous. The challenge was achieving adequate performance with soldiers who had limited time in service, who learned their roles relatively quickly, who needed simple, maintainable equipment. The 3-man crew was critical to this philosophy. Eliminating the loader meant fewer crew members needed per tank. For an army of conscripts, this mattered enormously. Training 400,000 men to crew 100,000 tanks was different from training 300,000 men to crew the same number of tanks. The difference was 100,000 trained personnel. The difference was training time, training infrastructure, training costs. Training 100,000 fewer crew members meant those personnel could be used elsewhere, could crew more tanks, could fill other roles. The efficiency gained was substantial. The training duration for tank crew was measured in months, not years. Conscripts arrived, learned basic military skills, then specialized training, tank operation, gunnery, maintenance. The curriculum was compressed, focused on essential skills, on achieving adequate performance quickly. The complexity of equipment affected training duration. Simpler equipment meant faster training, meant conscripts could achieve operational status sooner, could be deployed sooner. The 3-man crew fit this model, meant training fewer positions per tank, meant simpler crew coordination, meant faster achievement of basic competence. The autoloader enabled the 3-man crew, made it technically possible. The carousel was the solution, was how the loading function could be accomplished without a 4th crew member. The designers understood the trade-off, understood that placing the ammunition beneath the crew created vulnerability, but the vulnerability was weighed against the advantages, against the production benefits, against the training benefits, against the ability to field more tanks. The trade-off was considered acceptable. The design bureau operated within constraints, was directed to create tank that met specific requirements: low cost, high producibility, simple operation, adequate performance. The constraints were clear, were non-negotiable. The designers worked within these parameters, made choices that optimized for these priorities. The ammunition storage location was consequence of other priorities. The low profile required small turret. Small turret required eliminating loader. Eliminating loader required autoloader. Autoloader required carousel. Carousel fit beneath turret ring. The location followed from the chain of requirements, was consequence rather than primary choice. The designers weren't ignorant of vulnerability, weren't careless, understood that ammunition in crew compartment created risk, understood that penetration could cause catastrophic detonation, but also understood that alternative designs had different costs. Separate ammunition storage required larger turret. Larger turret meant higher profile. Higher profile meant easier to detect and hit, meant more weight, meant more expensive, meant slower production. The trade-offs were complex, Every choice had costs. The Soviet leadership accepted the trade-off consciously. The military doctrine accepted high casualties as reality of war. The planning assumptions included substantial tank losses. The operational concepts assumed breakthrough would be achieved despite losses. The individual tank wasn't precious, was expendable, was expected to be destroyed eventually. The goal was to achieve objectives before too many were destroyed, before the force was degraded below effectiveness, but some level of loss was assumed, was built into planning, was accepted. This assumption affected crew survivability priorities. Western doctrine viewed trained crews as more valuable than tanks, viewed experience as critical advantage, viewed crew survival as important enough to accept higher tank costs and lower production numbers. The logic was that a destroyed tank could be replaced relatively quickly. Industrial production could manufacture new tanks, but a dead crew took years to replace if counting training and experience. An experienced crew was force multiplier, made the tank more effective. Their loss was more significant than hardware loss. Therefore, protecting crews justified significant expense and design complexity. Soviet doctrine viewed this differently. Crews were considered more replaceable. Training was shorter, less sophisticated. Crews were expected to achieve adequate performance relatively quickly. The conscription system provided continuous flow of new personnel. The pipeline was constant. The loss of crew was unfortunate but acceptable. The loss of 3 men was sad, but not strategically significant if the tank accomplished its mission. If the breakthrough succeeded, if the advance continued, the cold calculus of mass warfare, of attrition warfare, of accepting casualties as cost of victory. The production economics reinforced this philosophy. The T-72 cost approximately 1/3 what Western contemporaries cost. The exact figures varied by exchange rates and accounting methods, but the general proportion was consistent. For the cost of 1 Western tank, the Soviet Union could produce 3 T-72s. For the cost of 100 Western tanks, 300 T-72s. The numerical advantage this created was substantial. Even accounting for lower individual effectiveness, the mass provided advantage. 3 against 1 meant overwhelming firepower, meant ability to absorb losses and continue, meant strategic flexibility. The production facilities were designed for mass output. Uralvagonzavod could produce dozens of tanks per month. The assembly line was organized for efficiency, for speed. The design was optimized for production. Components were standardized. Manufacturing processes were simplified. The supply chain was streamlined. The goal was maximum output at minimum cost. The facility achieved this, produced thousands of T-72s, continued production for decades. The industrial achievement was significant. Demonstrated Soviet manufacturing capability. Demonstrated ability to produce complex weapon systems in quantity. The maintenance philosophy also reflected doctrine. The T-72 was designed for field maintenance. The engine could be removed and replaced relatively quickly. A trained crew could perform the engine change in hours, in field conditions, with basic equipment. The running gear was accessible. Track replacement was straightforward. The systems were mechanical rather than electronic in early versions. Could be maintained without sophisticated diagnostic equipment. Could be repaired with basic tools. The design assumed that maintenance would occur in field, would be performed by crew or unit mechanics, would not always have factory-level support. The comparison with Western tanks illuminates the differences. The M1 Abrams entered American service in 1980, nearly a decade after the T-72. The design philosophy was opposite in key ways. The Abrams stored ammunition in a separate bustle compartment at the rear of the turret. The compartment was separated from the crew by armored doors. Blowout panels on top of the bustle were designed to vent any ammunition explosion upward and backward, away from the crew. If the ammunition detonated, The explosion would destroy the bustle, would blow the panels off. But the armored doors would protect the crew compartment. The crew could survive, could escape. The design accepted added weight, added complexity, added cost. Because crew survival was priority, the separate ammunition storage added approximately 1 ton to turret weight, required the bustle extension, required the blowout panel mechanism, required the armored doors between bustle and crew compartment. The complexity increased, the production cost increased, the maintenance requirements increased. But the U.S. military accepted these costs, valued crew protection sufficiently to accept the trade-offs, valued the training investment in each crew, valued the experience that accumulated over time, valued crew survival as strategic asset. The Abrams retained the 4-man crew, kept the human loader. The reasoning was reliability and flexibility. A human loader could adapt, could clear malfunctions, could load damaged ammunition, could improvise, could handle non-standard situations. The autoloader was mechanism that could fail, that could jam, that had limited flexibility. The human was more adaptable. The trade-off was larger turret, higher profile, more weight, higher cost. But these were acceptable because the human loader provided capabilities the autoloader couldn't match, provided redundancy, provided flexibility under combat conditions. The training for Abrams' crew was extensive. Tank commanders attended multi-month schools. Gunners trained for months. The investment in each crew member was substantial. The military wanted to preserve this investment, wanted experienced crews to survive, to accumulate knowledge, to become force multipliers. The design philosophy supported this, protected the investment, maximized the return on training expenditure by keeping crews alive. The internal volume of the Abrams was significantly larger. The crew had more space, could move more easily. Comfort was better, relatively speaking. Still not comfortable by civilian standards. Still cramped, but better than the T-72. The crew could endure longer periods in the tank, could maintain effectiveness better. The fatigue set in more slowly. The physical toll was less. The larger size was vulnerability in some ways, made the tank easier to spot, easier to hit, but the armor protection was substantial. The survivability when hit was better. The trade-off was considered worthwhile. The German Leopard 2 and British Challenger followed similar philosophy. Protected ammunition storage, 4-man crew, larger internal volume, emphasis on crew protection, higher individual cost, lower production numbers. The pattern among NATO tanks was consistent. Crew protection was paramount. Individual tank cost was higher. Production numbers were lower. But the philosophy was that superior tanks with superior crews would defeat larger numbers of lesser tanks. Quality over quantity, training over mass, survivability over producibility. The Gulf War in 1991 seemed to validate the Western approach. American M1 Abrams and British Challengers faced Iraqi T-72s. The engagement was one-sided. Coalition tanks destroyed Iraqi armor with minimal losses. The superior fire control, the superior optics, the superior training, the superior tactics, all contributed. The T-72s were outmatched. The crews often didn't survive. The turret toss phenomenon was documented extensively. The vulnerability was demonstrated clearly. But the context mattered. The coalition had air superiority, had better logistics, had professional crews with extensive training. The Iraqi crews were often conscripts, had minimal training, had poor maintenance, had inadequate support. The pure tank versus tank comparison was only part of the picture. Many factors contributed to the outcome. The design philosophy difference was one factor, important but not alone determinative. The Soviet philosophy wasn't irrational, wasn't stupid, was based on different assumptions. on different strategic requirements, on different resources. The Soviet Union couldn't match NATO tank for tank in quality, couldn't afford to, couldn't produce fast enough that way. The economy wouldn't support it, the industrial base wouldn't support it, so the strategy adapted to reality, emphasized what was achievable, what the Soviet system could produce, what Soviet doctrine could employ effectively. Mass production, simple design, acceptable casualties, overwhelming numbers. The doctrine assumed that war in Europe would be massive, would involve thousands of tanks, would be attritional, would result in heavy losses on both sides. The goal was to have enough tanks that even after heavy losses, sufficient force remained to achieve breakthrough, to exploit, to win. The calculation was strategic, was based on assessment of what war would require, of what would be needed to win. The individual tank loss was acceptable if collective force succeeded. The individual crew casualty was acceptable if the mission succeeded. The political dimension also mattered. The Soviet system was authoritarian. The leadership's accountability to population was limited. The acceptance of casualties didn't require democratic consensus, didn't require explaining to voters why losses were necessary. The decision-making was centralized, was based on strategic calculation rather than political pressure. This allowed accepting trade-offs that democratic societies might reject, allowed prioritizing mass over individual protection in ways that Western militaries couldn't or wouldn't. The T-72 succeeded at what it was designed to do, was producible in vast quantities, was simple to operate, was maintainable in field conditions, was exportable to client states, was affordable enough to field in the numbers Soviet doctrine required. The design met its goals, achieved its purposes. From the perspective of Soviet military planning, the T-72 was success, was exactly what was needed. The crew vulnerability was known, was accepted, was considered worthwhile trade-off for the advantages gained. The export market demonstrated the philosophy's appeal. Dozens of nations purchased T-72s. Nations that couldn't afford Western tanks, that needed armor but had limited budgets, that prioritized having tanks over having the best tanks. The T-72 filled this need, provided capability at accessible price, came with Soviet support, training, spare parts. The alternative, Western tanks, were more expensive, harder to obtain, came with political strings, came with requirements. The T-72 was available, was affordable, was adequate for many purposes. The crews who climbed into T-72s didn't make these decisions, didn't choose the design philosophy, didn't decide the trade-offs, just inherited the consequences, just worked with the tank they were given, just accepted the conditions that design created, just hoped the armor held, just hoped penetration didn't occur, just hoped luck favored them. The design philosophy was distant, was abstract, was made in design bureaus and military planning offices. But the consequences were immediate, were personal, were life or death, were experienced by every crew that entered the tank. That sat above the carousel, that worked in the cramped interior, that fought from this design, that died when penetration reached the ammunition. The sequence begins with penetration. An enemy projectile strikes the tank. Armor-piercing round. Anti-tank missile. The projectile has sufficient energy and design to defeat the armor. The composite armor in the front might stop it, might deflect it. But the side armor is thinner. The rear armor is thinner. The top armor is thinner. An attack from these angles has higher probability of penetration. Modern anti-tank missiles attack from above. Strike the thin top armor. Penetrate reliably. The projectile passes through the armor, enters the crew compartment. The projectile is moving at high velocity, is designed to penetrate, is designed to continue through obstacles. The projectile enters the interior. The the space where the crew works, where the ammunition is stored, where the carousel sits beneath the turret. If the projectile strikes the carousel, if it hits the propellant charges, the propellant detonates. The fabric bag is punctured. The propellant inside is exposed to the heat and impact of the penetrating projectile. The propellant ignites, begins burning, but the burning is confined, is rapid. The pressure builds instantly. The propellant bag ruptures completely. The propellant detonates rather than just burning. The explosion is immediate. One propellant charge detonating creates heat and pressure. The adjacent propellant charges are exposed to this, are subjected to the heat, to the pressure wave. The fabric bags rupture. The propellant inside detonates sympathetically. Those explosions trigger more. The progression moves through the carousel. All 22 propellant charges detonate. The timing is nearly simultaneous. The entire sequence from first detonation to last takes fractions of a second, perhaps 1/10 of a second, perhaps less. Faster than human perception, faster than awareness. The combined explosion releases enormous energy. 22 propellant charges, each containing several kilograms of explosive propellant. The total explosive equivalent is dozens of kilograms, detonating in the turret basket, in the crew compartment. The energy has to go somewhere, has to expand. The explosion creates pressure wave, creates heat, creates expanding gases. The volume of gas created is enormous, needs space to expand into. The hull beneath the explosion is strong, is armored. The sides of the turret are armored. The energy cannot easily escape downward or sideways. The path of least resistance is upward, through the turret ring. The turret is heavy, weighs several tons, but is not bolted down, sits on the turret ring, can rotate on the ring. The connection is mechanical, but not structural in the sense of being permanently fixed. The turret can be removed for maintenance, sits in place through weight and mechanical connection, but can be separated. The explosion pushes upward. The pressure is enormous. The turret is lifted. The mechanical connections break. The turret ring separates. The turret is propelled upward. The energy of the explosion is sufficient to overcome the weight, to accelerate several tons of metal upward, to throw the turret into the air. The velocity varies depending on how much ammunition detonated, how the explosion vented, the specific conditions, but the turret leaves the hull, separates completely, becomes airborne. The height achieved varies. Some turrets travel 10 or 15 feet, land near the hull. Others travel much higher. Reports exist of turrets traveling over 100 feet. The verification of extreme heights is difficult, but the phenomenon is documented extensively. Turrets landing significant distances from hulls. Turrets found dozens of meters away. The energy required to throw several tons of metal these distances is enormous. Indicates the violence of the ammunition detonation, the amount of energy released. The crew dies instantly. Multiple causes of death occurring nearly simultaneously. The pressure wave from the explosion is fatal. The human body cannot survive the sudden pressure increase. The internal organs are damaged. The brain is damaged. Death is instant or near instant from pressure effects alone. The explosion also creates extreme heat. The fire consumes the interior. The crew is burned. But this occurs after death from pressure. The fragmentation is also present. The explosion creates fragments. Pieces of the carousel mechanism, pieces of ammunition. These fragments move at high velocity, penetrate. But again, this occurs after death from pressure. The crew has no time to react. The sequence from penetration to explosion is faster than human reaction time. The crew doesn't know what's happening, doesn't understand. One moment, they're in the tank, performing their duties. Next moment, they're dead. The instant nature of death is in some ways merciful. No suffering, no awareness of dying, no time to fear, no time to understand, just instant transition from alive to dead. The commander and gunner in the turret have zero survival probability. They're in the turret when it separates, when it's thrown into the air. If somehow they survived the initial explosion, survived the pressure and heat and fragmentation, they're now inside a several-ton metal object traveling upward at high velocity. When the turret lands, when it impacts the ground, the deceleration is violent, fatal. No one survives being inside a turret that's thrown and impacts. The driver in the hull sometimes survives if the explosion vents primarily upward, if the pressure wave doesn't extend fully into the driver's compartment, if the fragmentation doesn't reach the driver might survive the initial explosion, might be able to escape through the driver's hatch, might evacuate before fire consumes the hull. But this is uncommon. Most destroyed T-72s show evidence of complete crew casualties. The driver usually dies with the rest of the crew. But survival is possible in some circumstances, is the exception rather than rule. The visual result is distinctive. The hull remains on the ground, burned usually, often completely gutted by fire. The turret is separated, lies nearby or at distance, sometimes upside down, the turret ring on top, the gun tube pointing down or at angle, sometimes on its side. The shape is recognizable, clearly a turret, but separated from where it belongs. The sight is unmistakable, indicates exactly what happened, indicates ammunition detonation, indicates catastrophic kill, indicates total crew loss. The comparison to Western tanks is stark. An M1 Abrams with ammunition detonation looks different. The bustle is destroyed. The blowout panels are gone. The rear of the turret is damaged, but the turret remains on the hull, remains attached. The crew compartment is intact, separated from the ammunition storage by armored doors. The crew can survive, can escape, can walk away. The tank is destroyed, but the crew lives. The design difference is visible in the aftermath, in what the destroyed tank looks like, in whether the turret is attached, in whether the crew could have survived. The physics of the T-72 design make survival nearly impossible. The ammunition is in the crew compartment, not separated, not protected, not equipped with any mechanism to vent explosion away from crew. When the ammunition detonates, the crew is in the explosion, is surrounded by it, is subjected to the full violence of it. The design provides no protection, no escape, no possibility of survival. The penetration that reaches the carousel is fatal, always. The crew knows this, understands this, hopes it doesn't happen, hopes the armor stops penetration, hopes the enemy round doesn't strike the carousel, hopes luck favors them. But if penetration occurs in the wrong place, if the carousel is struck, if the propellant detonates, they die, instantly, inevitably. The design allows no other outcome. The T-72 was designed in the context of Soviet military doctrine. Understanding why it was designed the way it was requires understanding what the Soviet military believed about future warfare. What assumptions guided design decisions? What priorities determined trade-offs? Soviet doctrine assumed large-scale conventional war. War in Europe primarily, against NATO forces. The doctrine emphasized mass, overwhelming numbers, breakthrough operations. The concept was that Soviet armor would concentrate at specific points, would breach NATO defenses through sheer weight of numbers, would exploit breakthrough rapidly, would advance deep, would disrupt NATO's ability to respond, would win through speed and mass rather than through technological superiority of individual vehicles. This doctrine had roots in World War II experience. The Red Army had learned that numerical superiority could overcome tactical disadvantages, had learned that tank armies could exploit breakthroughs, could advance hundreds of kilometers, could encircle enemy forces, could win through operational tempo and mass. The T-34 had embodied this philosophy, was simple, was producible in enormous quantities, was good enough to accomplish missions despite individual limitations. The doctrine that emerged from this experience emphasized quantity, emphasized breakthrough, emphasized exploitation, emphasized accepting casualties to achieve objectives. The Cold War context reinforced this doctrine. NATO had technological advantages, had better electronics, had better fire control in many systems, had better training often. The Soviet Union couldn't match NATO tank for tank in quality. The industrial base couldn't produce tanks as sophisticated as Western designs at comparable cost. The economy couldn't support equivalent investment per vehicle. The technological gap was real, was acknowledged, was factored into planning. The Soviet answer was numbers. If NATO had better individual tanks, the Soviet Union would field more tanks, would overwhelm through mass, would accept higher loss rates, would rely on weight of numbers to achieve breakthrough. The calculation was strategic, was based on industrial capacity, on economic reality, on what was achievable given Soviet resources and technological base. This assumption drove design philosophy. The T-72 needed to be producible in vast quantities, needed to be simple enough that wartime production could expand rapidly, needed to be cheap enough that thousands could be afforded, needed to be simple enough that conscripts with minimal training could operate them effectively. Every design choice was evaluated through this lens. Does this choice make the tank more producible, more affordable, simpler to operate? If yes, the choice was favored. If no, the choice was reconsidered. The conscription system was fundamental to Soviet military planning. The Red Army relied on conscripts, young men serving mandatory terms, typically 2 years, sometimes 3. The turnover was constant. Experienced soldiers left service, new conscripts arrived. The training pipeline was continuous. The challenge was achieving adequate performance with soldiers who had limited time in service, who learned their roles relatively quickly, who needed simple, maintainable equipment. The 3-man crew was critical to this philosophy. Eliminating the loader meant fewer crew members needed per tank. For an army of conscripts, this mattered enormously. Training 400,000 men to crew 100,000 tanks was different from training 300,000 men to crew the same number of tanks. The difference was 100,000 trained personnel. The difference was training time, training infrastructure, training costs. Training 100,000 fewer crew members meant those personnel could be used elsewhere, could crew more tanks, could fill other roles. The efficiency gained was substantial. The training duration for tank crew was measured in months, not years. Conscripts arrived, learned basic military skills, then specialized training, tank operation, gunnery, maintenance. The curriculum was compressed, focused on essential skills, on achieving adequate performance quickly. The complexity of equipment affected training duration. Simpler equipment meant faster training, meant conscripts could achieve operational status sooner, could be deployed sooner. The 3-man crew fit this model, meant training fewer positions per tank, meant simpler crew coordination, meant faster achievement of basic competence. The autoloader enabled the 3-man crew, made it technically possible. The carousel was the solution, was how the loading function could be accomplished without a 4th crew member. The designers understood the trade-off, understood that placing the ammunition beneath the crew created vulnerability, but the vulnerability was weighed against the advantages, against the production benefits, against the training benefits, against the ability to field more tanks. The trade-off was considered acceptable. The design bureau operated within constraints, was directed to create tank that met specific requirements: low cost, high producibility, simple operation, adequate performance. The constraints were clear, were non-negotiable. The designers worked within these parameters, made choices that optimized for these priorities. The ammunition storage location was consequence of other priorities. The low profile required small turret. Small turret required eliminating loader. Eliminating loader required autoloader. Autoloader required carousel. Carousel fit beneath turret ring. The location followed from the chain of requirements. Was consequence rather than primary choice. The designers weren't ignorant of vulnerability, weren't careless, understood that ammunition in crew compartment created risk, understood that penetration could cause catastrophic detonation, but also understood that alternative designs had different costs. Separate ammunition storage required larger turret. Larger turret meant higher profile. Higher profile meant easier to detect and hit, meant more weight, meant more expensive, meant slower production. The trade-offs were complex. Every choice had costs. The Soviet leadership accepted the trade-off consciously. The military doctrine accepted high casualties as reality of war. The planning assumptions included substantial tank losses. The operational concepts assumed breakthrough would be achieved despite losses. The individual tank wasn't precious, was expendable, was expected to be destroyed eventually. The goal was to achieve objectives before too many were destroyed, before the force was degraded below effectiveness, but some level of loss was assumed, was built into planning, was accepted. This assumption affected crew survivability priorities. Western doctrine viewed trained crews as more valuable than tanks, viewed experience as critical advantage, viewed crew survival as important enough to accept higher tank costs and lower production numbers. The logic was that a destroyed tank could be replaced relatively quickly. Industrial production could manufacture new tanks, but a dead crew took years to replace if counting training and experience. An experienced crew was force multiplier, made the tank more effective. Their loss was more significant than hardware loss. Therefore, protecting crews justified significant expense and design complexity. Soviet doctrine viewed this differently. Crews were considered more replaceable. Training was shorter, less sophisticated. Crews were expected to achieve adequate performance relatively quickly. The conscription system provided continuous flow of new personnel. The pipeline was constant. The loss of crew was unfortunate, but acceptable. The loss of 3 men was sad, but not strategically significant if the tank accomplished its mission. If the breakthrough succeeded, if the advance continued, the cold calculus of mass warfare, of attrition warfare, of accepting casualties as cost of victory. The production economics reinforced this philosophy. The T-72 cost approximately 1/3 what Western contemporaries cost. The exact figures varied by exchange rates and accounting methods, but the general proportion was consistent. For the cost of 1 Western tank, the Soviet Union could produce 3 T-72s. For the cost of 100 Western tanks, 300 T-72s. The numerical advantage this created was substantial. Even accounting for lower individual effectiveness, the mass provided advantage. 3 against 1 meant overwhelming firepower, meant ability to absorb losses and continue, meant strategic flexibility. The production facilities were designed for mass output. Uralvagonzavod could produce dozens of tanks per month. The assembly line was organized for efficiency, for speed. The design was optimized for production. Components were standardized. Manufacturing processes were simplified. The supply chain was streamlined. The goal was maximum output at minimum cost. The facility achieved this, produced thousands of T-72s, continued production for decades. The industrial achievement was significant. Demonstrated Soviet manufacturing capability. Demonstrated ability to produce complex weapons systems in quantity. The maintenance philosophy also reflected doctrine. The T-72 was designed for field maintenance. The engine could be removed and replaced relatively quickly. A trained crew could perform the engine change in hours, in field conditions, with basic equipment. The running gear was accessible. Track replacement was straightforward. The systems were mechanical rather than electronic in early versions. Could be maintained without sophisticated diagnostic equipment. Could be repaired with basic tools. The design assumed that maintenance would occur in field, would be performed by crew or unit mechanics, would not always have factory-level support. The comparison with Western tanks illuminates the differences. The M1 Abrams entered American service in 1980, nearly a decade after the T-72. The design philosophy was opposite in key ways. The Abrams stored ammunition in a separate bustle compartment at the rear of the turret. The compartment was separated from the crew by armored doors. Blowout panels on top of the bustle were designed to vent any ammunition explosion upward and backward, away from the crew. If the ammunition detonated, the explosion would destroy the bustle, would blow the panels off, but the armored doors would protect the crew compartment. The crew could survive, could escape. The design accepted added weight, added complexity, added cost, because crew survival was priority. The separate ammunition storage added approximately 1 ton to turret weight, required the bustle extension, required the blowout panel mechanism, required the armored doors between bustle and crew compartment. The complexity increased, the production cost increased, the maintenance requirements increased. But the U.S. military accepted these costs, valued crew protection sufficiently to accept the trade-offs, valued the training investment in each crew, valued the experience that accumulated over time, valued crew survival as strategic asset. The Abrams retained the 4-man crew, kept the human loader. The reasoning was reliability and flexibility. A human loader could adapt, could clear malfunctions, could load damaged ammunition, could improvise, could handle non-standard situations. The autoloader was mechanism that could fail, that could jam, that had limited flexibility. The human was more adaptable. The trade-off was larger turret, higher profile, more weight, higher cost. But these were acceptable because the human loader provided capabilities the autoloader couldn't match, provided redundancy, provided flexibility under combat conditions. The training for Abrams' crew was extensive. Tank commanders attended multi-month schools. Gunners trained for months. The investment in each crew member was substantial. The military wanted to preserve this investment, wanted experienced crews to survive, to accumulate knowledge, to become force multipliers. The design philosophy supported this, protected the investment, maximized the return on training expenditure by keeping crews alive. The internal volume of the Abrams was significantly larger. The crew had more space, could move more easily. Comfort was better, relatively speaking. Still not comfortable by civilian standards. Still cramped, but better than the T-72. The crew could endure longer periods in the tank, could maintain effectiveness better. The fatigue set in more slowly. The physical toll was less. The larger size was vulnerability in some ways, made the tank easier to spot, easier to hit, but the armor protection was substantial. The survivability when hit was better. The trade-off was considered worthwhile. The German Leopard 2 and British Challenger followed similar philosophy. Protected ammunition storage, 4-man crew, larger internal volume, emphasis on crew protection, higher individual cost, lower production numbers. The pattern among NATO tanks was consistent. Crew protection was paramount. Individual tank cost was higher. Production numbers were lower, but the philosophy was that superior tanks with superior crews would defeat larger numbers of lesser tanks. Quality over quantity, training over mass, survivability over producibility. The Gulf War in 1991 seemed to validate the Western approach. American M1 Abrams and British Challengers faced Iraqi T-72s. The engagement was one-sided. Coalition tanks destroyed Iraqi armor with minimal losses. The superior fire control, the superior optics, the superior training, the superior tactics, all contributed. The T-72s were outmatched. The crews often didn't survive. The turret toss phenomenon was documented extensively. The vulnerability was demonstrated clearly, but the context mattered. The coalition had air superiority, had better logistics, had professional crews with extensive training. The Iraqi crews were often conscripts, had minimal training, had poor maintenance, had inadequate support. The pure tank versus tank comparison was only part of the picture. Many factors contributed to the outcome. The design philosophy difference was one factor, important but not alone determinative. The Soviet philosophy wasn't irrational, wasn't stupid, was based on different assumptions, on different strategic requirements, on different resources. The Soviet Union couldn't match NATO tank for tank in quality, couldn't afford to, couldn't produce fast enough that way. The economy wouldn't support it, the industrial base wouldn't support it, so the strategy adapted to reality, emphasized what was achievable, what the Soviet system could produce, what Soviet doctrine could employ effectively. Mass production, simple design, acceptable casualties, overwhelming numbers. The doctrine assumed that war in Europe would be massive, would involve thousands of tanks, would be attritional, would result in heavy losses on both sides. The goal was to have enough tanks that even after heavy losses, sufficient force remained to achieve breakthrough, to exploit, to win. The calculation was strategic, was based on assessment of what war would require, of what would be needed to win. The individual tank loss was acceptable if collective force succeeded. The individual crew casualty was acceptable if the mission succeeded. The political dimension also mattered. The Soviet system was authoritarian. The leadership's accountability to population was limited. The acceptance of casualties didn't require democratic consensus, didn't require explaining to voters why losses were necessary. The decision-making was centralized, was based on strategic calculation rather than political pressure. This allowed accepting trade-offs that democratic societies might reject, allowed prioritizing mass over individual protection in ways that Western militaries couldn't or wouldn't. The T-72 succeeded at what it was designed to do, was producible in vast quantities, was simple to operate, was maintainable in field conditions, was exportable to client states, was affordable enough to field in the numbers Soviet doctrine required. The design met its goals, achieved its purposes. From the perspective of Soviet military planning, the T-72 was success, was exactly what was needed. The crew vulnerability was known, was accepted, was considered worthwhile trade-off for the advantages gained. The export market demonstrated the philosophy's appeal. Dozens of nations purchased T-72s, nations that couldn't afford Western tanks, that needed armor but had limited budgets, that prioritized having tanks over having the best tanks. The T-72 filled this need, provided capability at accessible price, came with Soviet support, training, spare parts. The alternative, Western tanks, were more expensive, harder to obtain, came with political strings, came with requirements. The T-72 was available, was affordable, was adequate for many purposes. The crews who climbed into T-72s didn't make these decisions, didn't choose the design philosophy, didn't decide the trade-offs, just inherited the consequences, just worked with the tank they were given, just accepted the conditions that design created, just hoped the armor held, just hoped penetration didn't occur, just hoped luck favored them. The design philosophy was distant, was abstract, was made in design bureaus and military planning offices, but the consequences were immediate, were personal, were life or death, were experienced by every crew that entered the tank, that sat above the carousel, that worked in the cramped interior, that fought from this design, that died when penetration reached the ammunition. The T-72 was designed for open warfare, for fields, for plains, for the European battlefield where Soviet doctrine assumed war would occur. The design parameters reflected this assumption. The armor protection was optimized for frontal engagements. The gun was designed for long-range combat. The mobility was adequate for cross-country movement. The design made sense for the intended environment, for tank versus tank combat in open terrain, for the warfare Soviet planners expected. Urban combat was different. The environment changed everything. The advantages of the T-72 design were negated. The vulnerabilities were exposed and exploited. The urban terrain created conditions where the tank's weaknesses became fatal, where the ammunition storage vulnerability became maximum liability, where crew survival became improbable. The city of Grozny in Chechnya became demonstration of urban vulnerability. In December 1994, Russian forces entered the city. The goal was to retake control from Chechen separatist forces. The Russian military expected relatively quick success, expected that armored forces would overwhelm opposition, expected that the conflict would be brief. The reality was different, was catastrophic for Russian armor, was one of the worst defeats for armored forces in urban combat in modern warfare. The Chechen fighters understood urban combat, understood how to use the terrain, understood the vulnerabilities of tanks in cities. The tactics were simple but effective. Ambush from buildings, attack from above, attack from behind. Target the sides and rear where armor is thin. Use multiple attack points simultaneously. Divide the tank crew's attention. Overwhelm their ability to respond. The buildings provided concealment, provided positions for fighters to wait, to watch, to select targets. The fighters would position in buildings along routes tanks would travel, would wait for the tanks to enter the kill zone, would coordinate attacks. Multiple fighters, multiple positions. When the tank was in position, the attacks would begin. RPGs fired from different positions, from different heights. The tank crew couldn't respond to all threats simultaneously, couldn't defend all directions. The turret could only face one direction. The guns could only engage one target at a time. The attacks targeted the sides of tanks, the rear, the top. These areas had thinner armor, were vulnerable to RPG penetration. The RPG-7 was widely available, was simple to use, was effective against side armor. The warhead was shaped charge, designed to penetrate armor. The penetration depth was sufficient to defeat T-72 side armor at close range. The urban environment allowed close range, allowed attacks from meters away, from positions above the tank where the thin top armor was exposed. When penetration occurred, the results were familiar. The projectile entered the crew compartment, struck the ammunition. The propellant detonated. The explosion was catastrophic. The turret lifted off. The crew died. The pattern repeated throughout Grozny. Tanks destroyed, turrets separated, crews killed, the losses mounted. Russian armored units suffered casualties that were unsustainable. Units lost most of their tanks, lost most of their crews. The offensive stalled, eventually failed, had to be restarted with different tactics, with more infantry support, with more careful advance. The lessons from Grozny were harsh. Urban combat required different approach, required infantry to clear buildings, required support from artillery and air power, required slower advance, required tanks to be protected by infantry, required accepting that tanks in cities were vulnerable, that the environment favored defenders, that losses would be high if tanks were used improperly. But the fundamental vulnerability remained. The T-72's design problem couldn't be solved through tactics, through training, through better combined arms coordination. These things helped, reduced losses, but didn't eliminate the core issue. The ammunition storage was unchanged. The carousel was still beneath the crew. The propellant charges were still in fabric bags. The vulnerability to catastrophic detonation was still present. The urban environment just exposed it more clearly, made exploitation easier, made the consequences more frequent. Syrian cities saw similar patterns years later. Government T-72s operating in urban areas, opposition fighters using anti-tank weapons, modern guided missiles in some cases, simple RPGs in others, the attacks from buildings, from prepared positions, the targeting of sides and rear, the penetrations, the explosions, the turret toss, the destroyed tanks, the pattern repeating, the same vulnerability, the same exploitation, the same results. The urban environment made several aspects worse. The close ranges meant more weapons could penetrate, meant even older anti-tank weapons were effective. The buildings provided multiple attack positions, provided concealment until the moment of attack. The narrow streets restricted tank movement, made retreat difficult, made maneuvering difficult. The height advantage from buildings meant attacks from above, attacks on the thin top armor. The combination created environment where T-72 vulnerability was maximized, where crew survival was minimized. The psychological impact on crews was significant. Tank crews knew urban operations were most dangerous, knew survival rates were poor, knew that urban combat meant high probability of ambush, high probability of penetration, high probability of death. Some crews tried to refuse urban missions, tried to avoid being assigned. The fear was rational, was based on observed casualties, was based on understanding of vulnerability, was based on knowing that the tank's design made survival unlikely if hit in cities. The training attempted to address urban combat, taught tactics, taught combined arms coordination, taught awareness, but couldn't solve the fundamental problem, couldn't redesign the tank in the field, couldn't change the ammunition storage, couldn't eliminate the vulnerability, could only teach crews how to minimize exposure, how to work with infantry, how to reduce probability of ambush. But probability couldn't be eliminated. Eventually, in extended urban operations, most tanks would be hit. Most crews would face the situation they feared, would face penetration, would face ammunition detonation, would face instant death. The urban battlefield became a place where T-72 design philosophy faced ultimate test, where the trade-offs made for open warfare were exposed as fatal in close terrain, where the crew sat above ammunition that couldn't be protected, that couldn't be vented safely, that would kill them when struck. The open battlefield allowed maintaining distance, allowed using frontal armor, allowed mitigating some vulnerability through tactics and positioning. The urban battlefield allowed none of this, required entering close terrain, required exposing sides and rear, required accepting that ambush was probable, that penetration was likely, that survival was uncertain. The maximum vulnerability was realized, was demonstrated, was paid for by crews who had no choice but to enter cities, who had no choice but to operate in an environment that maximized every flaw in their vehicle's design. The vulnerability was known early, was understood by Soviet designers, was evident in testing, was confirmed in early combat use. The question arose repeatedly. Why wasn't the ammunition storage redesigned? Why wasn't the carousel moved? Why wasn't protection added? Why did the vulnerability persist for 5 decades? The answers are complex, are institutional, are economic, are technical, are about how military procurement works, about how existing systems persist. The fundamental issue is that fixing the ammunition storage requires redesigning the tank. The carousel isn't a component that can be easily modified, isn't a part that can be swapped out, is integral to the entire design. The turret is designed around the carousel, the hull is designed to accommodate it. The autoloader mechanism is built into the turret basket. Changing this means changing everything, means redesigning the turret, redesigning the hull, redesigning the ammunition storage system, redesigning the loading mechanism, essentially creating a new tank, Creating a new tank is expensive. The development costs are enormous. The design work takes years. The testing takes years. The tooling for production takes years. The training for crews and maintainers takes years. The entire process from concept to fielding takes a decade or more. The investment is measured in billions. For a nation with existing inventory of thousands of tanks, this investment is difficult to justify, especially when the existing tanks still function, still fulfill their basic purpose, still can destroy enemy armor, still can accomplish missions. The existing inventory creates inertia. Thousands of T-72s exist, in Russian service, in the service of dozens of other nations. These tanks are paid for, are in service, are supported by existing logistics, by existing training, by existing doctrine. Replacing them requires not just new tanks, requires new logistics system, new training, new doctrine, new maintenance infrastructure, new spare parts supply. The total cost exceeds just the cost of the tanks themselves, includes the entire support system. The pragmatic calculation is whether the cost of replacement exceeds the cost of accepting the vulnerability. The military planners calculate. Compare. The vulnerability causes casualties. But how many? In what percentage of engagements? Against what opponents? In what scenarios? If the tank is used correctly? If the tactics are proper? If the engagement occurs at long range? If the frontal armor is presented? The vulnerability might be manageable, the casualties might be acceptable, the cost of replacement might exceed the value gained. The alternative approach is incremental upgrade. Add reactive armor, improve fire control, improve optics, improve engine. Each upgrade improves some aspect of the tank, makes it more effective, helps it avoid being hit, helps it hit first. The upgrades are cheaper than replacement, are faster to implement, can be done to existing vehicles. The approach is gradual, is affordable, is achievable, but doesn't address the fundamental ammunition storage problem, doesn't eliminate the vulnerability, just works around it, tries to minimize the probability it's exploited. The T-90 represents this approach, is essentially upgraded T-72. Better systems, better protection in some areas, better fire control, better optics, but same basic design, same autoloader, same carousel, same ammunition storage, same vulnerability. The T-90 shows turret toss when destroyed. Recent conflicts demonstrate this. The upgrade improved many things, didn't improve the one thing that kills crews. The fundamental design remained. The carousel remained. The vulnerability remained. Russia has developed the T-14 Armata, a truly new tank with fundamentally different design. The crew is in the hull, all 3 crew members forward in protected capsule. The turret is unmanned. The ammunition is in the turret. If the ammunition detonates, the crew is separated, is protected. The design addresses the T-72's vulnerability directly, eliminates it through complete redesign. The T-14 is what fixing the problem actually looks like. Requires completely new vehicle, completely new design philosophy. But the T-14 production has been limited. The costs are high. The technical challenges are significant. The numbers produced are small, dozens rather than thousands. The T-14 might eventually replace the T-72. But this process will take decades if it happens at all. For now, the T-72 remains in service, remains the primary Russian tank, remains the vehicle that crews must use. The modern solution exists, is proven, is available, but isn't deployed in numbers, isn't replacing the vulnerable design in the near term. Other nations with T-72s face similar decisions. Replacing thousands of tanks is expensive, is often beyond budget. The alternative is continuing to use what exists. Accepting the vulnerability, training crews, hoping tactics and doctrine minimize the exploitation. Some nations have upgraded their T-72s, have added reactive armor, have improved some systems, but none have solved the carousel problem. None have eliminated the fundamental vulnerability. The technical and economic barriers are too high, the investment too large, the existing inventory too valuable to discard. The psychological and ethical dimensions are uncomfortable. Military leaders know the vulnerability, know that crews are at risk, know that the design kills crews when penetrated, but also know that replacing the design is expensive, is slow, is difficult. The calculation becomes cost-benefit. How many casualties are acceptable to avoid the cost of replacement? How much is crew safety worth in monetary terms? These questions don't have comfortable answers, but must be answered implicitly through procurement decisions, through whether to invest in replacement or continue with existing design. The crews don't make these decisions, don't control procurement, don't decide whether to develop new tanks or upgrade old ones. Just inherit the results. Just climb into the T-72s that are available, that are assigned. Just work with the design that exists. Just hope the vulnerability isn't exploited. Just accept that their safety was weighed against other priorities, that the cost of fixing the design was considered too high, that they will crew the vulnerable tank because the alternative is too expensive, too slow, too difficult. The institutional decisions made far from them, by people who won't crew the tanks, who won't sit above the carousel, who won't die if the propellant detonates. The decisions rational perhaps from institutional perspective, from budget perspective, from procurement perspective, but the crews live with the consequences, die with the consequences, pay for the decisions with their survival, with their lives, with the instant of catastrophic explosion that ends everything. That validates the vulnerability. That demonstrates the cost of the decision not to fix, not to replace, not to prioritize their survival over economic and institutional considerations. The T-72 remains in active service worldwide. The numbers are substantial. Russia operates thousands. Former Soviet states operate them. Syria, Iraq, India, Poland, Czech Republic, Algeria, Libya, Iran. The list extends across continents. The production history and export market mean the T-72 and its variants are distributed globally, are present in numerous militaries, will remain in service for years, likely decades. The modern variants include upgrades and improvements. The T-72B was an upgraded version from the 1980s. Better armor, better fire control. The T-72B3 is a recent Russian upgrade. Modernizes fire control systems, adds reactive armor, improves engine in some versions, improves optics significantly. The upgrades make the tank more effective in some ways. Better ability to see at night, better ability to hit targets at range, better protection against some threats from the reactive armor. But the fundamental design remains. The carousel is unchanged, the ammunition storage is unchanged. The crew still sits above 22 propellant charges. The charges are still in fabric bags. The autoloader mechanism is essentially the same as the 1971 original. Some electronic improvements to the controls, but the mechanism itself, the carousel itself, unchanged. The vulnerability persists. The modern T-72B3 shows turret toss when destroyed. The recent conflicts demonstrate this clearly. The upgrades improve some capabilities, didn't improve the one that determines crew survival after penetration. The T-90 represents more extensive upgrade. Was initially designated T-72BU, was upgraded sufficiently to receive new designation. The T-90 has better armor package, better fire control, better active protection in some versions, better thermal sights. The improvements are significant. The tank is more capable than base T-72, is more effective on modern battlefield. But underneath the improvements, underneath the new systems, the same autoloader, the same carousel, the same ammunition storage, The T-90 is evolutionarily related to T-72, shares the fundamental design, shares the vulnerability. Recent combat demonstrates this. Russian T-90s in Ukraine show the same destruction pattern as T-72s. Turrets separate from hulls, land meters away. The distinctive evidence of carousel detonation, the modern variant, with all its improvements, with its upgraded systems, still suffers from the same catastrophic vulnerability, still kills its crew when penetration reaches the ammunition. The decades of upgrades, the improvements in technology, the better optics and fire control and armor, none addressed the core issue, none fixed the problem that kills crews. The T-14 Armata is Russia's answer to the vulnerability, is fundamentally different design. The crew capsule in the hull. Forward position, armored, separated from the turret. The turret is unmanned, contains the gun, contains the autoloader, contains the ammunition. But no crew. If the ammunition detonates, if the turret is destroyed, the crew is separate, is protected, survives, can evacuate. The design philosophy is completely different, prioritizes crew survival, accepts complexity and cost for this protection. The T-14 uses autoloader still, but the autoloader is an unmanned turret. The ammunition detonation doesn't kill crew, just destroys turret. The vehicle is mission killed, cannot continue fighting, but the crew lives, can evacuate, can fight another day. The design recognizes that trained crews are valuable, that protecting crews is worth additional cost. The philosophy shift, from Soviet doctrine of expendable crews to recognition that crews matter, that crew survival is important, but the T-14 production is limited. The numbers built are small. Dozens of vehicles, some parade appearances, some testing, limited operational deployment. The reasons for limited production are unclear from outside. Cost is likely factor. Technical challenges likely factor. The Russian military-industrial complex faces constraints, economic sanctions, technical limitations, production priorities. Whatever the reasons, the result is clear. The T-14 isn't replacing the T-72 yet, isn't available in numbers, isn't solving the vulnerability problem for most Russian tank crews. The other nations operating T-72s face different situations. Most cannot afford to develop new tanks, cannot afford to purchase Western tanks in large numbers. The T-72s they have are what's available, are what's affordable. The choice is to upgrade them or to operate them as is. Most choose some level of upgrade. Reactive armor, better fire control if affordable, better communications. The upgrades help. Make the tanks more survivable against some threats, make them more effective in some scenarios. But don't eliminate the carousel vulnerability. Don't redesign the ammunition storage. Don't solve the fundamental problem. India operates over 2,000 T-72s, has upgraded many to T-72 Ajaya standard. Better systems, better protection, better night fighting capability, but same basic design. Same autoloader. Poland operates hundreds, has upgraded to various standards. Czech Republic, Algeria, Syria, Iraq, all operate T-72s. All face the same vulnerability. All have crews that sit above carousel ammunition. All accept the risk. All hope their crews don't face penetration, don't face the instant of catastrophic detonation. The export market continues. Some nations still purchase T-72 variants. The tanks are affordable, are available, come with support from Russia or licensed producers. The price is fraction of Western tanks. For nations with limited defense budgets, the T-72 is accessible option, is proven platform, has decades of service history. The vulnerability is known, is accepted as trade-off for affordability, for availability, for compatibility with existing systems if the nation already operates Soviet-designed equipment. The continued use means Continued casualties. Every conflict involving T-72s demonstrates the vulnerability, shows the turret toss, shows the crew deaths. The pattern repeats. Will continue repeating. The tanks remain in service, remain in combat. The crews continue climbing inside, continue sitting above the carousel, continue hoping penetration doesn't occur, continue dying when it does. The modern era, the 21st century, the age of advanced technology. The T-72 persists, the vulnerability persists, the deaths continue. The question of how long the platform will remain in service is significant. The answer is uncertain, but likely measured in decades. Russia has enormous inventory. Thousands of T-72s. Upgrading these is cheaper than replacing. The upgrades extend service life, maintain capability. The T-14 might eventually replace them, but the timeline is extended. Production is slow. Costs are high. The replacement process will take decades if it happens at all. The T-72 will likely remain primary Russian tank through the 2030s, possibly beyond. The 50-year-old design continuing, the vulnerability continuing, the risk to crews continuing. Other nations face similar timelines. Replacing large tank fleets is a generational project, takes decades, requires sustained investment. Many nations cannot afford this, will operate T-72s for foreseeable future, will continue to accept the vulnerability, will continue to train crews on the platform, will continue to deploy them in combat when conflicts occur. The global distribution of T-72s means the design will remain relevant, will remain in use, will remain killing crews when penetrated, for years, for decades. The crews entering service now, training on T-72s now, will face the same vulnerability, the same risk, the same probability of instant death if penetration reaches the carousel. Nothing in their experience will be different from crews 50 years ago. The same cramped interior, the same heat or cold, the same noise, the same knowledge of sitting above ammunition, the same hope that armor holds, the same instant of death if it doesn't. The design they inherit, the conditions they accept, the risk they live with, are unchanged from 1971. The technology around the tank improved. The world changed. The nature of warfare evolved. But inside the T-72, inside the experience of being crew member, everything remains familiar, remains constant, remains dangerous in exactly the same ways. The persistence of the design, the continuation of the vulnerability, the ongoing casualties, all indicate how difficult changing established systems is, how institutional inertia works, how existing inventory creates its own justification for continuation. The T-72 exists in thousands, therefore must be supported, must be maintained, must be used, must be kept operational. The investment in the platform is enormous, sunk cost, but also ongoing cost. Supporting the platform, training crews, maintaining vehicles. The investment justifies continuation, makes replacement difficult, makes accepting the vulnerability seem pragmatic, seem necessary, seem inevitable. The modern variants are better tanks than the original in many ways. See better, hit more accurately, are better protected against some threats, but remain fundamentally flawed in the same way, remain vulnerable in the same way, remain fatal to crews in the same way. The improvements are real, are valuable, but don't address what matters most. Don't protect the crew when penetration occurs. Don't prevent the catastrophic ammunition detonation. Don't stop the turret toss. Don't save lives when the carousel is struck. The vulnerability that defined the original design, that killed crews in the 1980s and 90s and 2000s and 2020s, remains, persists, continues, will continue, for years, for decades, for as long as the T-72 platform remains in service, for as long as nations operate these tanks, for as long as crews climb inside. Sit above the carousel. Hope luck favors them. Die instantly when it doesn't. Behind the technical descriptions, behind the design philosophy, behind the statistics and the conflicts, are individuals, young men mostly, often conscripts, often 19 or 20 years old, sometimes younger, assigned to tank crews, trained on the T-72, sent into combat, expected to perform, expected to fight, expected to accept the risks, expected to climb into a machine that would kill them instantly if penetrated in the wrong place. The crew members didn't choose the T-72, didn't select this tank over alternatives, were assigned, were given the equipment their military provided, were trained on what was available. The choice was to serve or not to serve. Once serving, the equipment was determined. The tank was what it was. The crew worked with what they had, adapted to the conditions, learned the systems, performed their duties. The knowledge of vulnerability varied. Some crews understood the ammunition storage, understood what the carousel meant, understood that sitting above propellant charges was dangerous, had technical training that explained the system, understood the risk intellectually. Other crews had less understanding, knew the tank could be destroyed, knew combat was dangerous, but didn't understand the specific mechanism, didn't know about sympathetic detonation, didn't know about turret toss, just knew tanks were dangerous. That crew members died. That war was risky. The psychological response to knowledge varied among those who understood. Some developed fatalism, accepted that risk was inherent, accepted that combat meant danger, focused on what could be controlled, on proper operation, on good tactics, on situational awareness, on engaging threats before threats engaged them. The fatalism wasn't defeat, wasn't despair, was acceptance, was pragmatism, was recognition that worry didn't help, that fear didn't protect, that the job required functioning despite risk, required performing despite danger. Other crew members struggled with anxiety. The knowledge of vulnerability created fear, created stress, made every engagement feel threatening, made every enemy tank feel lethal, made every ambush position feel fatal. The anxiety affected performance sometimes, made crew members hesitate, made them overly cautious, made them less effective. The fear was rational, was based on real risk, but was still debilitating, still interfered with function, still made the job harder. The crew bonds were important. 3 men in close quarters, dependent on each other completely. The relationships mattered. A crew that functioned well together, that trusted each other, that communicated effectively, could manage the stress better, could support each other, could maintain morale despite conditions. A crew with personality conflicts suffered more. The close quarters amplified tensions, made disagreements worse, made the stress harder to manage, made everything more difficult. The young age of many crew members is significant. 19-year-old conscripts, operating complex vehicles in combat. The maturity required is substantial. The responsibility is enormous. The consequences of mistakes are fatal. Some young men rose to the challenge, performed well, demonstrated competence beyond their years. Others struggled, were overwhelmed, were not ready for the responsibility, for the danger, for the reality of combat. But ready or not, they were crew members, were expected to perform, were sent into combat, were subjected to the same risks as more experienced crews. The families knew some risk. Knew military service was dangerous. Knew combat could kill, but often didn't understand specific risks. Didn't know about carousel vulnerability. Didn't know about turret toss. Just knew their son or husband or brother was in tank crew, was in combat zone, was at risk. The worry was present, was constant, was manageable only by hoping, by trusting that training would protect, that equipment would protect, that luck would favor. that their loved one would come home. When crew members died in T-72s, when the ammunition detonated, when the turret separated, the death was instant. This is repeated because it's important. The crew didn't suffer, didn't burn to death, didn't have time to fear, didn't have awareness of dying. One moment operational, next moment gone. The instant death is in some ways merciful. No agony, no terror, no prolonged dying. Just instant transition, but for families, for fellow crew members, for units. The loss was still complete, still final, still devastating. The cause of death in these cases was partially the enemy, was partially the penetrating projectile, but was also partially the design. The crew died because the ammunition storage made survival impossible, died because the propellant was in the crew compartment, died because the design accepted crew vulnerability as trade-off for other advantages. The distinction matters. Death from enemy action is one thing. Death from design flaw is another. The crew died fighting, but also died because the vehicle they were assigned to serve in was fundamentally flawed in a way that made death inevitable when certain conditions occurred. The ethical dimension is uncomfortable. Military leaders knew the vulnerability, knew that crews would die, made decisions to continue fielding the design anyway. The decisions were rational from institutional perspective, from budgetary perspective, from strategic perspective, but placed crews at risk knowingly, accepted casualties that might have been preventable with different design. The calculation of acceptable casualties, of acceptable risk, of acceptable cost in lives versus cost in resources. These calculations are necessary in military planning, but are uncomfortable, raise questions about value of individual lives versus collective missions. Questions without easy answers, questions that were answered implicitly through continuations of T-72 deployment, through acceptance of the vulnerability, through decision not to replace the design. The crew members who survived close calls, who were in tanks that were hit but didn't penetrate, or penetrated but didn't strike Carousel, carried knowledge forward, understood how close they came, understood that luck saved them, that next engagement luck might not favor them. Some became more cautious, some became more fatalistic, some refused to think about it, pushed the experience away, continued operating, continued functioning. But the knowledge was there, was unavoidable, was part of their experience going forward. The understanding of mortality, of randomness, of how thin the line between survival and death was, how much depended on factors beyond control. The memorial to T-72 crew members doesn't exist in single location, exists in multiple locations, in military cemeteries, in hometown memorials, in family memory. The crew members who died aren't distinguished from other military casualties typically, are honored as soldiers, as service members, as those who gave their lives in service. The specific manner of death, the specific cause, the design vulnerability that contributed. These aren't highlighted, aren't commemorated specifically. The deaths are folded into broader category of combat casualties, of those who died in service, of sacrifice made for nation, the specific circumstances, the specific preventability, the specific design choice that contributed. These are technical details, are not part of public memory typically, are not part of how the deaths are understood or honored. But the deaths were real. The crew members were real. The young men who climbed into T-72s, who sat above Carousel ammunition, who hoped armor would hold, who died when it didn't. Each was individual, had family, had aspirations, had future that ended instantly when propellant detonated, when turret separated, when design vulnerability was exploited. The human cost, the individual cost, cannot be fully captured in statistics, in technical descriptions, in design analysis, can only be acknowledged, can only be recognized, can only be remembered. The crew members who died because they were assigned to crew a tank that was fundamentally flawed. That would kill them if penetrated in vulnerable location. That provided no protection, no chance, no survival, just instant death. The cost paid by individuals, for design decisions made by others, for institutional priorities, for economic constraints, for strategic requirements. The cost measured in lives, in families disrupted, in futures ended, in potential never realized. The human cost of the T-72's vulnerability. The T-72 has been in service for over 50 years, has been used in combat extensively, has demonstrated its capabilities and limitations, has accumulated history, has shaped outcomes, has affected the lives of hundreds of thousands of crew members, has killed tens of thousands when the vulnerability was exploited. The story of the T-72 is technical and human both, is about design choices and their consequences, is about the men who lived and died with those choices, is about the persistence of flawed systems, about the difficulty of change, about the cost measured in lives of institutional inertia. The design achieved its goals. The T-72 was producible in vast quantities, over 25,000 manufactured, tens of thousands more produced under license. The numbers exceeded any competing design. The production capability demonstrated Soviet industrial strength, demonstrated ability to field overwhelming armored forces. The tank was simple enough for conscripts to operate, was maintainable in field conditions, was exportable to nations with limited technical infrastructure. The design was successful by the metrics that mattered to Soviet military planning, by the standards of mass production, of quantity over quality, of acceptable casualties. The goals were met. The doctrine was supported. The design worked as intended. But the cost was measured in crew lives. The vulnerability that was accepted as trade-off for producibility, for low cost, for small size. That vulnerability killed crews consistently. Killed them in the 1980s and 90s and 2000s and 2020s. Killed them in Iraq and Chechnya and Syria and Ukraine. The pattern consistent. The mechanism unchanged. The result predictable. The crews who died instantly when ammunition detonated, who had no chance when penetration reached the carousel, paid the cost of the design trade-offs, paid with their lives, with their futures, with everything. The turret toss became symbol, became visual shorthand for T-72 vulnerability, the separated turret lying meters from hull, the distinctive evidence of catastrophic ammunition detonation, the sight that appeared in every conflict, in every theater, against every opponent, the consistency indicating fundamental design issue, indicating that this wasn't bad luck, wasn't circumstantial, was inherent to how the tank was built, to where the ammunition was stored, to how the propellant was contained, to the absence of protection, of blast venting, of crew separation from ammunition. The turret toss was consequence, was inevitable result of design decisions, was predictable, was known, was accepted. The comparison with Western tanks illuminates different philosophy, different priorities, different answers to same questions. How do you protect crew? Western answer was separate ammunition, blast panels, 4-man crew, higher cost, lower production numbers. Soviet answer was autoloader, Carousel Beneath crew, 3-man crew, lower cost, higher production numbers. Neither answer was objectively correct. Both reflected different assumptions, different resources, different doctrine, different values about what mattered most. The results differed. Western crews survived ammunition detonations sometimes. Soviet crews never did. The difference was design philosophy made tangible, made measurable in survival rates. The persistence of the design, the continuation for 50 years, the ongoing use, all indicate how difficult military procurement is, how slowly systems change, how existing inventory creates its own justification. The T-72 exists, therefore must be supported, therefore continues. The vulnerability is known, is documented extensively, is demonstrated repeatedly, but is not sufficient reason to replace thousands of tanks, is not sufficient to justify the investment. The cost of replacement exceeds the cost of accepting casualties. From institutional perspective, from budgetary perspective, the calculation is rational perhaps, is pragmatic, but places crews in vehicles that will kill them when penetrated, accepts their deaths as cost of avoiding replacement cost. The trade-off made, continues being made, will continue until replacement finally occurs. If replacement occurs, the lessons are multiple, about design trade-offs, about how decisions made in peacetime affect outcomes in war, about the persistence of flawed systems, about the difficulty of change, about the cost paid by individuals for institutional decisions. The T-72 demonstrates that design matters, that where you put ammunition matters, that crew protection matters, that trade-offs have consequences, that accepting vulnerability means accepting casualties, that the casualties are real people, are young men with families, with futures, who die instantly when the design's flaw is exploited. The future of the platform is uncertain in detail but clear in general. The T-72 will remain in service for years, likely decades. Thousands exist. Replacement is expensive, slow, difficult. The T-14 Armata might eventually replace them, but production is limited. Timeline is extended. For foreseeable future, the T-72 remains in Russian service of dozens of other nations, remains in combat, remains vulnerable, remains fatal to crews when penetration occurs. The vulnerability that was present in 1971, that killed crews in every subsequent decade, remains present, remains unchanged, remains killing crews today, will remain killing crews tomorrow and next year and for years beyond. Until finally, eventually, the platform is replaced, the design is retired, the vulnerability is eliminated through replacement rather than through fix, through new vehicle rather than through retrofit, because fixing the T-72's ammunition storage is impossible, is creating new tank, is what the T-14 represents, is what replacement actually requires, the memory of the T-72, the understanding of what it meant, should include both, should include the technical achievement, the production numbers, the capability, the service history, but should also include the vulnerability, the casualties, the crew members who died, the design flaw that made survival impossible, the trade-offs that placed crews at risk, the persistence of the flaw despite knowledge, despite documentation, despite decades of evidence. The complete picture, the full understanding, includes success and failure both, includes achievement and cost both, includes what the tank accomplished and what it cost the crews who operated it. The crews climbing into T-72s today, in Russia, in other nations, face the same risk, sit in the same positions, above the same carousel, with the same propellant charges, in the same fabric bags, the same vulnerability, the same hope that armor holds, the same instant death if penetration reaches ammunition. Their experience connects to crews 50 years ago, the continuity across decades, across conflicts, across the world, the shared experience of being T-72 crew member, of accepting the conditions, of managing the heat or cold, of enduring the noise, of living with the knowledge of what sits beneath, of hoping luck favors them, of dying instantly if it doesn't. The experience unchanged, the vulnerability unchanged, the cost unchanged, measured in lives, in families disrupted, in futures ended, in the instant when penetration occurs, when propellant detonates, when turret separates, When crew dies, the cost of the T-72, the cost of the design choices, the cost paid by crews for 50 years, for years to come, until finally the design is no longer used, until finally replacement occurs, until finally crews no longer sit above carousel ammunition, no longer face instant death from design vulnerability, no longer pay the price of decisions made in 1971. Made in Design Bureau in Nizhny Tagil, made to achieve low profile, to enable three-man crew, to enable mass production. The decisions that created the T-72, that created its vulnerability, that created the turret toss, that created the cost measured in crew lives across 5 decades of service. The machines are quiet now where we've been. The T-72s are parked, engines off, crews elsewhere. The hatches closed, the interior empty. The carousel beneath sits ready, the ammunition in place, the propellant charges in their positions, waiting for the next crew, the next mission, the next engagement, the design unchanged, the vulnerability persistent, the risk continuing. We've moved through this history together, from the outside of the tank to the interior, from the design philosophy to the human experience. From the mechanism that loads the gun to the catastrophic explosion that ends everything. From the conflicts that demonstrated the vulnerability to the reasons it was never fixed. The story is complete. The understanding is developed. The technical and human aspects are both present, both acknowledged, both remembered. The T-72 achieved what it was designed to achieve. Provided the Soviet Union with tank that could be produced in overwhelming numbers, that could equip entire armies, that could fulfill doctrine's requirements. The success was real, was significant, was achievement of design and production and deployment. But the success came with cost. The cost paid by crews, the cost measured in instant deaths when ammunition detonated, when turrets separated, when the design's vulnerability was exploited. The cost was known, was accepted, was considered worthwhile trade-off for the advantages gained. The calculation rationale, perhaps, from institutional perspective, but fatal for crew members, for individuals, for young men who climbed inside, who sat above the carousel, who hoped, who died. The understanding of the T-72 requires holding both. The achievement and the cost, the success and the failure, the capability and the vulnerability, the design that armed nations and killed crews, the machine that served for 50 years and killed for 50 years, the platform that continues and the casualties that continue. Both are true, both are real, both are part of the story, both deserve acknowledgement, deserve recognition, deserve to be understood, deserve to be remembered, for those who rest now, for those whose futures ended in the instant of detonation, for those whose families mourned, for those whose potential was never realized. The memory persists, the acknowledgement matters, the recognition that their deaths were partly enemy action, partly design flaw, partly institutional decision to accept vulnerability rather than pay replacement cost. The complete understanding includes this, includes that the crews who died were served equipment that was fundamentally flawed, that would kill them when penetrated, that provided no protection, no chance, no survival, just instant death. The understanding includes this truth, this reality, this cost. The T-72 continues in service, continues facing modern threats, continues demonstrating the same vulnerability. The turrets continue separating from hulls. The crews continue dying instantly. The pattern continues, will continue, for years, for decades potentially, until replacement finally occurs, until the design is finally retired, until crews no longer face this specific vulnerability, this specific risk, this specific instant death from ammunition detonation beneath them. The continuation is reality, is present fact, is ongoing cost, measured in ongoing casualties, in ongoing losses, in ongoing deaths that are preventable but not prevented, that are known but accepted, that are documented but continued. Rest now. The story is told, the machine is understood, the crews are acknowledged, the cost is recognized. The T-72's half-century of service, of achievement, of vulnerability, of casualties is documented, is remembered, is understood in its complexity, in its achievement and cost both. The crews who served, who died, who survived, who climbed into this machine, who accepted its conditions, who faced its risks, who paid its cost, are part of history now, are part of the record, are part of what the T-72 means, what it represents, what it cost, in technical terms and human terms both, in design achievement and crew casualties both, in institutional success and individual tragedy both. The complete story, the full understanding, the T-72, the tank that armed armies, the tank that killed crews, the machine that continues, the vulnerability that persists, the cost that continues, for now, for years ahead, until finally, eventually, the design is retired, the vulnerability is eliminated through replacement. The story reaches conclusion. The crews no longer face this risk, this cost, this instant death from design flaw 50 years old. The end that comes eventually. But not yet. Not now. Not for years. The T-72 continues. The vulnerability continues. The cost continues. Measured in lives, in turrets thrown skyward, in crews who don't survive, who never survive, who cannot survive. Inside a T-72,